Equilibrium 1. The essential idea. Many reactions are reversible. These reactions will reach a state of equilibrium when the rates of forward and reverse reaction are equal. The position of equilibrium can be controlled by changing the conditions. Nature of science. Obtaining evidence for scientific theories. Isotopic labelling and its use in defining equilibrium. There's common language across different disciplines. For example, the term dynamic equilibrium is used in other contexts, but not necessarily with the chemistry definition in mind. Employing quantitative reasoning. Experimentally determined rate expressions for forward and backward reactions can be deduced directly from the Stoichiometric equations and Lissatelli's principle. Theory of knowledge. The career of Fritz Haber coincided with the political upheavals of 2 world wars. He supervised the release of chlorine on the battlefield in World War I and worked on the production of explosives. It makes you think about how does the social context of scientific work affect the methods and findings of science? And should scientists be held morally responsible for the applications of their discoveries? In the bonding unit we did previously, you looked at this example of an equilibrium system. We looked at how oxygen could be converted to ozone, but also at the same time ozone can be converted to oxygen. We need to think about what equilibrium means in this context, and also we need to know what is required for an equilibrium to exist. Here are some examples of common equilibria. In our blood, hemoglobin, which is bound to a hydrogen ion, will react with oxygen to form a hemoglobin oxygen complex, and it will release a hydrogen ion. But at the same time, obviously oxygen's got to be released into your organs and muscles and all the cells of your body, so the oxygen must also be able to, the hemoglobin must also be able to give up the oxygen and release it. So the reaction must be able to go this way too. It goes this way, obviously your lungs, when the hemoglobin's picking up the oxygen from your lung tissue. Here we have this fantastic reaction which allows us to capture nitrogen from the air and make ammonia. And this really is a vital reaction that Mr. Haber, we just talked about previously, discovered. And homeostasis, you biologists in there will know that many systems in the body are in homeostasis. They are balanced. Have a look, please. Press pause, go on YouTube and watch this clip. You can see the link at the bottom there. Some requirements for chemical equilibrium. 1. They must be reversible reactions. Some examples would be a phase change. Ice can turn to water, water can turn back to ice depending on the temperature. Salts. You can dissolve salts in water if you cool down the liquid enough, or if you concentrate the salt enough, the salt will precipitate back out. You've got synthesis and decomposition of ionic compounds. Acid-base indicators are quite obvious ones. You can change colour of solution and a reaction is taking place. The indicator will be one colour in one form and a different colour in another form, and then go between the two equilibrium depending on the pH. And finally you've got thermochromic properties. You might have seen these heat sensitive sheets that if you warm up you see different colours appearing, then you remove the heat and that colour disappears. Another requirement is you need closed systems. So if you've got reactions involving a gas, the gas can't escape. It must be within a sealed container or the equilibrium will be broken as the gas escapes. It's kind of common sense. Aqueous reactions, where there's no gases, can take place in open containers, and you kind of just if there's you're losing a tiny bit by evaporation, but don't worry about too much, it mainly being the solvent to be evaporating. And the Earth can also be considered a closed system, and the reactions taking place within the atmosphere are all within the atmosphere. No gases are escaping or being brought in apart from the odd meteor. Some characteristics of chemical equilibria. Firstly, the rate of the forward reaction will equal the rate of the reverse reaction. If we look at this graph here, we've got rate on the y-axis, time on the x. As time goes by, the rate of the forward reaction will slow as the concentration of the reactants lowers. If you remember, concentration affects the rate of reaction. So as the concentration of those reactants lowers, the rate should slow down of the forward reaction. But as products are being formed, then the concentration of those increase and the reverse reaction will start to increase in rate. So over time, the rate of the reverse reaction increases, and you can see here the rate of the forward reaction decreases as the concentration of the reactants decreases till it hits equilibrium. The rate of the reverse reaction, there's no products to begin with, then as the product concentration builds up, the rate of this reverse reaction increases until it forms an equilibrium. And then you can see the rate for both are identical. That is the equilibrium state. 2a, we have macroscopic properties are constant. For example, you have constant pressure at equilibrium, constant volume at equilibrium, constant colour at equilibrium, and constant pH and constant conductivity. And that makes sense because you've got the same concentration of reactants and same concentration of products. So all their properties will be constant. 2b, reactant and product concentrations are constant, but they aren't necessarily equal. So have a look here. You can see concentration on the left hand side. Obviously the reaction starts, you've got no products, and products are being formed, so you get a great concentration. But eventually hits equilibrium and you have a constant amount of products. Constant concentration of products. Conversely, reactants, you start off with a high concentration. As they react and become products, you get lower and lower concentration of reactants until they hit a constant concentration. Conversely, you could end up with, say, the products, you could end up with a higher concentration of products than you did with reactants. And that will all just depend on the equilibrium balance. The system is dynamic. You might get in your head, or you might think, okay, they've reached equilibrium, so there's no reaction taking place anymore. It's fixed. Well, it's not, it's dynamic. At the microscopic or molecular level, the changes are still occurring. The forward reaction and backward reactions are still occurring. Reactants are being converted to products, and products are being converted back to reactants constantly. 4. Equilibrium can be approached from either direction. And that kind of makes sense. So you've got some reactants, and that's basically what you're starting with. Okay? And then the reactants will react to form products. And at a certain point, those products will start reacting to form the reactants. And you end up with a balance, an equilibrium. You could just as easily, instead of starting with reactants, you could instead just get the products. If you mix them together, then the same equilibrium will be set up. Press pause and you can just fill that little graph in to show this, please. And you only can do that if you're in class, so we'll skip that. Okay, the equilibrium law. Consider this equilibrium system. We've got hydrogen gas reacting with iodine gas to give hydrogen iodine gas. The concentration of all species at equilibrium was measured in several trials. So we've got the concentration, for trial 1, 2, 3, 4 for the two reactants and the product. Okay, so when equilibrium was reached in trial 1, you had 0.0222 moles per decimeter cubed of hydrogen, 0.0222 moles per decimeter cubed of iodine, and 0.156 for the hydrogen iodide. Okay, you get the idea. What generalizations, if any, can you make about the equilibrium concentrations? Well, you can see straight away, I guess, that if you say look at trial 1 and trial 4, we're kind of just doubling the concentration for trial 1 to trial 4. The concentration of iodine doubles, and the concentration of the hydrogen iodide also doubles. So you can see a pattern there. Okay, 1 minute. I found the heating up. I'll close them down. With this in mind, we'll have to think about the equilibrium law. Is there a quantitative relationship for equilibrium concentrations? So we've got the concentration of these three, of the two reactants and the reactant. And remember, it doesn't matter which trial you do, there should be an equilibrium set up. Okay, so the relationship of this, the product, to the two reactants should be constant. So we want to find out which one of these three would the product, or the concentration of the product, or the concentration of the two reactants, give a sensible result. Or we've got the concentration of the product squared, because remember we had this coefficient here. Or alternatively, we could put that coefficient in front here. Press pause, do the maths, and then we'll discuss it. Okay, hopefully you got a similar answer to this, and then you can see straight away that we put the coefficients up as a power next to the concentrations, and we do this. We can see we've done it here because obviously all of these are almost identical. So this is giving us a constant, an equilibrium constant. The general law, or the equilibrium expression, is written as so. Let's say we've got two reactants, two products. You've got the coefficients in lowercase, reactants in uppercase. Products go on the top, and their coefficients become powers. The equilibrium constant is temperature dependent. The square brackets again we use for molar concentrations at equilibrium. And solids are omitted from the equilibrium constant expression. And this is because you can't compress their density. You can't compress them, so the density remains the same, or in other words, their concentration remains the same. You can't squish them together. Okay, state the equilibrium expression for these equilibrium systems. Press pause and do it. I'll give the answers in a second. Okay, so we've got coefficient of 2 for the product, so ammonia squared. We've got a coefficient of 1, a coefficient of 3, so nitrogen has 1, hydrogen has a coefficient of 3. Next. We've got methanol, coefficient of 1, it's the product, so it goes on top. Hydrogen, coefficient of 2, carbon monoxide, coefficient of 1, so no need to add anything. Got ammonium chloride, giving us ammonia and hydrochloric acid. You can see straight away that this is just not included. Why is it not included? I hear you say, why? Well, that's because it is a solid, and so it's not included. So the products go in, and there's no need to include the reactant. Over here, you can see straight away before I even give you the answer, we've got a solid there, and we have a solid here. So we've got the product, copper ions on top, and we've got the silver ions at the bottom there, and we've got the coefficient of 2. What about over here? In this case, you could have 1 over the reactants because the product is a solid. Let's do some problems. Calculating Kc values given equilibrium concentrations. You've got the system with nitrogen and hydrogen in equilibrium with ammonia. At certain temperature, the equilibrium concentrations of the reactions are given. So we've got the concentration of both reactants and the product. We want to calculate the value of the equilibrium constant at this temperature. And we know it's at equilibrium, so we can write down equilibrium constant. Products go on top. We can see that the product has a coefficient of 2, so the concentration squared. Nitrogen, coefficient of 1. Hydrogen, coefficient of 3. Plug in the numbers and do the math to get your answer. Okay, finding an equilibrium concentration given Kc and other concentrations. We've got an equilibrium system of oxygen and ozone, and we're given the equilibrium constant. If the equilibrium concentration of oxygen gas is 4.0 times 10 to the minus 4, what's the equilibrium concentration of ozone at 25 degrees Celsius? Write out the equilibrium constant. We've got products on top. Oh, wrong way around. Products on top. And got a coefficient of 2 squared, oxygen on the bottom because it's the reactants, and you can see coefficient of 3, so this is cubed. We're given the equilibrium constant here, so that can go straight in here. We've got oxygen, so it goes underneath, and then you can do the math to get your answer. What does a Kc value tell us? What does an equilibrium constant value tell us? Well, the general equation for an equilibrium system is as follows. And we know it's roughly the concentration of products over the concentration of reactants. So, if we recall that solids are excluded, equilibrium constants are used, can be used to work out the magnitude, to work out the relative concentrations of products to reactants at equilibrium. So the magnitude of Kc is important. The larger this is, okay, the bigger it is, the higher concentration of products we have. If this is a very small number, a fraction indeed, then we know we'd have a higher concentration of reactants compared to products. So this number does tell us about the balance of the equilibrium. It tells us if we've got a higher concentration of products or a higher concentration of reactants. If a Kc value is around about 1, then obviously the amount of products the concentration of products must be roughly the same as the concentration of reactants. So the concentration of products at equilibrium is roughly the same as the concentration of reactants at equilibrium. So over time, the reactants and the products will be roughly the same. Neither the reactants nor the products are favoured in this equilibrium. They will be roughly the same. Here we have equilibrium constant values above 1. So obviously, if it's above 1, then the number on top must be bigger than the number on the bottom. And so we must have a higher concentration of products compared to reactants. Therefore, the concentration of products is higher than the concentration of reactants. And in this case, if I had a concentration time graph, the reactants would, as they react, the concentration lowers till they reach equilibrium. And as products are formed, their concentration will increase. In this case, they will go above the concentration of the reactants because they have a greater value. The position of the equilibrium favours the products. So the equilibrium lies to the right. Bear in mind, if a K value is much, much greater than 1, the reaction is essentially going to completion. So if you've got a value where the products value is gigantic and the reactance is very small, it'll be nearly 1. The reactance gone to completion. What about if a value is smaller than 1? In this case, for our fraction, the reactance must be bigger than products. So the reactants have a greater concentration than the products. If we look at this graph, the reactants as they start reacting will form products, and you get less reactants, and then they'll reach equilibrium. As the products are formed, their concentration increases, but they reach equilibrium at a lower concentration than the reactants reached equilibrium here. The position of the equilibrium favours the reactants, and the equilibrium lies to the left. Bear in mind, if a K value is really, really small, much smaller than 1, then the reaction barely proceeds at all. If we look at the fraction, if you've got a much, much higher reactant concentration than product concentration, well then you've made hardly any products, and you've still got lots of reactants. So the reaction is not taking place, or it is barely proceeding. Ooh, what does a Kc value tell us? Let's have a look here. In this example, for each of the following equilibria, what does the magnitude of Kc value suggest about the reaction at equilibrium? Press pause, have a think. Okay, for the first one, we've got nitrogen and oxygen giving us nitrogen monoxide, and we have a very small Kc value. This tells us that we have a high concentration of reactant and a low concentration of product. So the reaction is barely taking place. It is, we mainly have reactants here. The balance is to the left. Next, same reaction, but it's at 700 degrees Celsius. Now we see we've got a larger Kc value. This means the reaction has moved to the right. We have a higher concentration of product than we do of these reactants. So this time the balance is shifted to the right hand side. What about these? Let's look at 3 and 4 together, shall we? We've got lead chloride giving us 2 ions. We've got lead iodide giving us 2 ions. Now, yeah, I can hear you wanting me to interrupt YouTube, shouting at me, in fact, saying, but look, we've got solids here and solids here, and they do not, they aren't included in our equilibrium constant. So we put reactants on the top, essentially over 1, and we can see that in the case of lead, we have a higher equilibrium constant with lead chloride compared to lead iodide. So this reaction here, slightly more lead chloride will dissolve in an aqueous solution than lead iodide will. Example 2, arrange the following in order of their excuse me, arrange the following in order of their tendency to go towards completion. All equilibrium constant values are given at 25 degrees Celsius. Press pause, have a think. Okay, so we want to arrange them in order of the tendency to go to completion. So we need to find ones which have a higher concentration of product. So higher concentration of product means a greater equilibrium constant. Straight away you can see number 1 has the greatest equilibrium constant, and then the next biggest value is number 3, and obviously then last we'd have number 2. The 2 didn't work very well. Example 3, let's consider these equilibrium pairs and their Kc values. We kind of looked at these a second ago. Let's just think about it a bit more. The reaction between nitrogen and oxygen gas in the atmosphere has implications for the production of pollutants like nitrogen dioxide. This gas contributes to the production of acid rain and smog. Okay, when you can't see too well over the harbour, often nitrogen monoxide is involved there, and it can trigger quite a lot of asthma attacks in the city too. So what is the significance of these Kc values at given temperatures in terms of air quality? Oops. Well, obviously, at low temperatures, 25 degrees, nitrogen and oxygen will not react together very well to give us nitrogen monoxide. You can see it's a very small value, so the balance of the equation is very much to the left-hand side. There'll be far more reactants than there will be products. So it'll be far more nitrogen gas, the inert gas, and oxygen, which we need to breathe. Conversely, at 700 degrees, we've got a high Kc value, or high constant value. And so the reaction now is tipped over this way. Nitrogen gas and oxygen gas are going to start reacting together. The reactants will form products, and we'll get a higher concentration of the products than we will reactants. And so we're going to get a lot of this poisonous nitrogen monoxide. B. Chloride salts of heavy metals are slightly soluble and form equilibria with their dissolved ions, as shown in these equations, and we looked at this a second ago as well. Which salt is more soluble in water at 25 degrees and why? Have a think about these two. Press pause. Okay, well, straight away we can see the lead chloride, as discussed, has a higher equilibrium constant. Therefore, we're going to get more products from here as compared to the lead iodine reaction. And so we know that lead chloride is more soluble than lead iodide. Which anion would be more effective at removing lead ions from a contaminated body of water? Well, if the top reaction leans more to the right, then this reaction must lean more to the left. So if you want to take lead out of solution to form a solid, you'd want whichever of these, you want the smallest value of these to make more left leaning, more reactant leaning. So it'll draw the iodine out, the lead ions out. So obviously it'll be this lower one because it has a lower equilibrium constant. Manipulating equations. If we rewrite an equilibrium equation, how does the K value change? Let's consider the equilibrium system 2AB with A2 gaseous and B2 gaseous. We've got a K equilibrium constant value of 9 at 25 degrees. And so we would write out the equilibrium constant as A2 times B2 over AB squared. What would happen if we were to reverse this equation? Just rewrite it the other way round. So this time, instead of AB giving us A2 B2, we're going to have the A2 B2 here giving us the AB. What would the equilibrium constant be? Well, let's write the thing out. You've got your AB squared over A squared over B squared. So obviously it's just going to be 1 over K1. And so if we had 9, then it's going to be 1 over 9 or 0.11. Right, this time we'll take this one and we're going to multiply all coefficients in equation 1. If this, we're going to multiply them all by 2. So instead of having 2, 1, 1, we're going to have 4, 2, 2. What will be the equilibrium constant here? Right, so in this, instead of having 1, 1, 2 here, we're going to have 2, 2, 4. We can rearrange this if you do a bit of maths and just put the power outside there, which will be the same as having k to the power. So 9 squared is going to give us 81. What if we divided all coefficients by 2? So we're going to have AB in equilibrium with half A2 and half B2. What will K4 be? You can probably guess. We're going to write it out with the new powers there, taken from the coefficients. Do a bit of math, rip those out there. I'm going to be putting you 2. And that's going to give us the square root of K1. So the square root of 9, which is 3. Okay, to summarise manipulating equations, we're going to look at this table. If you reverse an equation, then the effect on the equilibrium constant is to have 1 over that equilibrium constant. If we multiply coefficients by n, then we raise the equilibrium constant to the power of n. If we divide coefficients by n, then it's the equilibrium constant to the cube, to the root of n, to the root of n. And if we add two equations together, you just multiply the two equilibrium constants together. And we will look at that in more detail in the next unit, which is acids and bases. And that's the end of this presentation. Splendid.